So can you speak to the uncountable infinities?
Yeah,
so what are the
absolutely.
integers and the real numbers, and
Right.
what is the line that Cantor was able to find?
So maybe there's one more step I want to insert before doing that, which
Great.
is the rational numbers. So we did pairs of natural numbers,
Mhm.
right? That's the train car basically. But maybe it's a little bit informative to think about the fractions, the set of fractions or rational numbers. Because a lot of people maybe have an expectation that maybe this is a bigger infinity because the rational numbers are densely ordered. Between any two fractions, you can find another fraction, right? The average of two fractions is another fraction. And so sometimes people, it seems to be a different character than the integers, which are discretely ordered, right? From any integer, there's a next one and a previous one and so on. But that's not true in the rational numbers. And yet, the rational numbers are also still only a countable infinity. And the way to see that is actually it's just exactly the same as Hilbert's train again, because every fraction consists of two integers, the numerator and the denominator. And so if I tell you two natural numbers, then you know what fraction I'm talking about. I mean, plus the sign issue. I mean, if it's positive or negative. But if you just think about the positive fractions, then you have the numbers of the form p over q, where q is not 0. So you can still do 3 to the p times 5 to the q. The same idea works with the rational numbers. So this is still a countable set. And you might think, well, every set is going to be countable because there's only one infinity. I mean, if that's a kind of perspective maybe that you're um, adopting, but it's not true. And that's the profound achievement that Cantor made, is proving that the set of real numbers is not a countable infinity. It's a strictly larger infinity, and therefore there's more than one concept of infinity, more than one size of infinity.
So let's talk about the real numbers. What are the real numbers? Why did they break infinity, the
Right.
countable infinity?
Right.
Looking it up on Perplexity, real numbers include all the numbers that can be represented on the number line, encompassing both rational and irrational numbers. We've spoken about the rational numbers, and the rational numbers, by the way, are, by definition, the numbers that can be represented as a fraction of two integers.
That's right. So with the real numbers, we have the algebraic numbers. We have, of course, all the rational numbers. The integers and the rationals are all part of the real number system, but then also we have the algebraic numbers like the square root of 2 or the cube root of 5 and so on. Numbers that solve an algebraic equation over the integers, those are known as algebraic numbers. It was an open question for a long time whether that was all of the real numbers or whether there would exist numbers that are the transcendental numbers. The transcendental numbers are real numbers that are not algebraic.
And we won't even go to the surreal numbers, about which you have a wonderful blog post. We'll talk about that a little bit later.
Oh, great. So it was Louisville who first proved that there are transcendental numbers, and he exhibited a very specific number that's now known as the Louisville constant, which is a transcendental number. Cantor also famously proved that there are many, many transcendental numbers. In fact, it follows from his argument on the uncountability of the real numbers that there are uncountably many transcendental numbers. So most real numbers are transcendental.
And again, going to Perplexity, transcendental numbers are real or complex numbers that are not the root of any non-zero polynomial with integer or rational coefficients. This means they cannot be expressed as solutions to algebraic equations with integer coefficients, setting them apart from algebraic numbers.
That's right. So some of the famous transcendental numbers would include the number pi, the 3.1415925 and so on. So that's a transcendental number. Also, Euler's constant, the e, like e to the x, the exponential function.
So you could say that some of the sexiest numbers in mathematics are all transcendental numbers.
Absolutely, that's true. Yeah. Although, I don't know, square root of 2 is pretty...
Square root. All right. So it depends. Let's not... Beauty can be found in all the different kinds of sets. But yeah.
And if you have a kind of simplicity attitude, then, 0 and 1 are looking pretty good too. So, and they're definitely not...
Sorry to take that tangent, but what is your favorite number? Do you have one?
Oh, gosh.
Is it 0?
Did you know there's a proof that every number is interesting? You can prove it because
Yeah? What's that proof look like?
Yeah,
How do you
okay.
even begin?
I'm going to prove to you that
Okay.
every natural number is interesting.
Okay.
I mean, 0 is interesting because, it's the additive identity, right? That's pretty interesting. And 1 is the multiplicative identity. So when you multiply it by any other number, you just get that number back, right? And 2 is, the first prime number. That's super interesting, right? And
Mhm.
okay, so one
Yeah.
can go on this way and give specific reasons, but I want to prove as a general principle that every number is interesting, and this is the proof. Suppose, toward contradiction, that there were some boring numbers. Okay,
Uh,
but if
okay.
there was an uninteresting number,
Yes.
then there would have to be a smallest uninteresting number.
Mhm. Yes.
But that's a contradiction because the smallest uninteresting number is a super interesting property to have. So therefore, there
Oh,
cannot
that's
be
good.
any boring numbers.
I'm gonna have to try to find a hole in that proof because there's a lot of baked in the word interesting. But yeah, that's beautiful.
Right.
That doesn't say anything about the transcendental numbers, about the real numbers. You just
That's right.
proved from just for
That's right.
natural
Yeah.
numbers.
Okay. So should we get back to Cantor's argument? Or
Sure,
okay.
you've masterfully avoided the question. Well, you basically said, "I love all numbers." Is
Yeah.
that what you said?
Basically, yeah.
Okay,
That's
all right.
what my
Back to
intention.
Cantor's argument. Let's go.
Okay. So Cantor wants to prove that the infinity of the real numbers is different and strictly larger than the infinity of the natural numbers. So the natural numbers are the numbers that start with 0 and add 1 successively. So 0, 1, 2, 3, and so on. And the real numbers, as we said, are the numbers that come from the number line, including all the integers and the rationals and the algebraic numbers and the transcendental numbers and all of those numbers altogether. Now, obviously, since the natural numbers are included in the real numbers, we know that the real numbers are at least as large as the natural numbers. And so the claim that we want to prove is that it's strictly larger. So suppose that it wasn't strictly larger. So then they would have the same size. But to have the same size, remember, means, by definition, that there's a one-to-one correspondence between them. So we suppose that the real numbers can be put into one-to-one correspondence with the natural numbers. So therefore, for every natural number n, we have a real number, let's call it r sub n. R sub n is the nth real number on the list. Basically, our assumption allows us to think of the real numbers as having been placed on a list, R1, R2, and so on. Okay, and now I'm going to define the number z, and it's going to be, the integer part is going to be a 0, and then I'm going to put a decimal place, and then I'm going to start specifying the digits of this number z. D1, D2, D3, and so on. And what I'm going to make sure is that the nth digit after the decimal point of z is different from the nth digit of the nth number on the list.
Mm-hmm.
Okay, so to specify the nth digit of z, I go to the nth number on the list, r sub n, and I look at its nth digit after the decimal point. And whatever that digit is, I make sure that my digit is different from it. Okay. And then I want to do something a little bit more, and that is I'm going to make it different in a way that I'm never using the digits 0 or 9. I'm just always using the other digits and not 0 or 9. There's a certain technical reason to do that. But the main thing is that I make the digits of z different in the nth place from the nth digit of the nth number. If you had drawn out the numbers on the original list, R1, R2, R3, and so on, and you made it, and they were each filling a whole row, and you thought about the nth digit of the nth number, it would form a kind of diagonal going down and to the right. And that, for that reason, this argument is called the diagonal argument, because we're looking at the nth digit of the nth number, and those exist on a kind of diagonal going down. And we've made our number z so that the nth digit of z is different from the nth digit of the nth number. But now it follows that z is not on the list because z is different from R1 because, well, the first digit after the decimal point of z is different from the first digit of R1 after the decimal point. That's exactly how we built it. And the second digit of z is different from the second digit of R2. and so on. The nth digit of z is different from the nth digit of r sub n for every n. So therefore, z is not equal to any of these numbers r sub n. But that's a contradiction because we had assumed that we had every real number on the list, but yet here is a real number z that's not on the list. Okay. And so that's the main contradiction.
And so it's a kind of proof by construction.
Exactly. So given a list of numbers, Cantor is proving. It's interesting that you say that, actually, because there's a kind of philosophical controversy that occurs as in connection with this observation about whether Cantor's construction is constructive or not. Given a list of numbers, Cantor gives us a specific means of constructing a real number that's not on the list, is a way of thinking about it. There's this one aspect which I alluded to earlier, but some real numbers have more than one decimal representation, and it causes this slight problem in the argument. For example, the number 1. You can write it as 1.0000 forever, but you can also write it as 0.999 forever. Those are two different decimal representations of exactly the same number.
And then you beautifully got rid of the zeros and the nines, therefore we don't need to even consider that,
Yes.
and the proof still works.
Exactly, because the only kind of case where that phenomenon occurs is when the number is eventually 0 or eventually 9. And so since our number z never had any zeros or nines in it, it wasn't one of those numbers. And so actually in those cases, we didn't need to do anything special to diagonalize. Just the mere fact that our number has a unique representation already means that it's not equal to those numbers. So maybe it was controversial in Cantor's day more than 100 years ago, but I think it's most commonly looked at today as, one of the initial main results in set theory, and it's profound and amazing and insightful and the beginning point of so many later arguments. And this diagonalization idea has proved to be an extremely fruitful proof method. And almost every major result in mathematical logic is using in an abstract way the idea of diagonalization. It was really the start of so many other observations that were made, including Russell's paradox and the halting problem and the recursion theorem, and so many other principles are using diagonalization at their core. So